Hello, my name is Mark McClure, and this presentation is on best practices for interpretation of DFIT tests for stress, permeability, and pore pressure. Here's a quick outline of this presentation. This presentation is going to be fairly long, maybe an hour and a half, and so you may want to skip around if there are different parts that you want to see. I'm going to start off by talking about why DFITs are performed, what are they, and what we hope to learn. Secondly, I'm going to talk quite a bit about changes in DFIT interpretation procedure that I will advocate in this presentation and that are based on several papers summarizing work that I've done with colleagues over the past 6 years. So specifically, in 2018, my company ResFrac did a joint industry study with a group of operators and one service company on DFIT interpretation, and I'm going to go through the method that we developed in that paper in this presentation, but also, very importantly, I'm going to discuss problems with a very widespread DFIT interpretation technique called the tangent method or holistic method. This is widely used, but it's turned out to be a very entrenched concept, and so it requires quite a bit of time to kind of deconstruct it and explain why we shouldn't use it, what are the problems, so that we can move forward, which is the second half of this presentation. Then I'll give a step-by-step interpretation procedure. I'll actually have an example of a field DFIT and go through it. Then next I'll talk about some challenges we can see in real data and assessing confidence in our interpretation. And finally, I'll finish with some just kind of practical curveballs I've seen in real data, things that can confuse as you're doing an interpretation. So I hope that you find this useful. Here are 3 key papers that I've written with different colleagues over the past few years. On the top left, you can see this paper written with Mukul Sharma and Ho-Jung Jung at University of Texas and Dave Kramer at ConocoPhillips. It's called the Fracture Compliance Method for Picking Closure Pressure. We did a follow-up paper called Reexamining Interpretations of Non-Ideal Behavior, as you can see in the lower left, where we looked at some more complicated scenarios. And then finally, the collaborative industry study that we performed in 2018 within ResFrac is over here on the right. You can see this URTeC paper from 2019 summarizing those results. So largely much of what I say today will draw upon the material in those papers. You'll see I have a lot of other references, and there's a list of references at the end of the presentation. First, some kind of high-level commentary here. What I'm going to talk about today is principally for fracture injection testing performed in low permeability formations, less than 10 microdarcies. And as I'll discuss later, there's a qualitative difference in the shape of the transients between low and high permeability formations and how they should be interpreted. Some of the procedures that I'm going to show today in the step-by-step procedure are completely standard. There's nothing new. Others are explicitly disagreeing with things that are often widely done in the industry. And some are incremental improvements. So I will try to differentiate between those. The entire step-by-step procedure that I'm going to provide can be implemented by an engineer in an Excel spreadsheet. In fact, I have an Excel spreadsheet that I'm happy to share with anyone who is interested in seeing it that goes through the full procedure. So it doesn't require any complex, specialized numerical modeling tool, even though it is based on results from numerical modeling tools. As much as possible, we want to try to minimize jargon, although that cannot be eliminated, and so I'm going to do my best. Another thing that I'm going to advocate here is focusing on the key interpretations: permeability, stress, pore pressure. I think there's a temptation to look at every single little wiggle on a plot. Of course, we like to do things like take derivatives and then multiply by things, and we have different plotting techniques designed to kind of accentuate very, very small changes in trends. And that can lead to a temptation of overinterpretation. And so to try to avoid that, we're not going to focus in on interpreting every little wiggle. Lastly, this presentation really focuses on interpretation, not operational aspects of practically how do you pump a DFIT. There are some other really nice references out there about that. For example, Kramer and Nguyen's 2013 paper. And finally, before I get started, I'm going to give a little bit of editorializing. I first started writing papers about DFIT in 2014. The compliance method concept, which identifies key problems with the tangent or holistic approaches, that was developed 6 years ago. And while the tangent method approach is still It's a lot less used than it was before. It's still probably the number one used approach in the industry. And it's interesting for me to ask, we really have put out some really clear and pretty unambiguous demonstrations of the fallacy of this concept, and it's been quite a few years now, and yet largely much of the industry has not shifted. And so, that experience and many others I've had, I think anybody who's in this industry for a while understands that our culture makes it very difficult for people to admit mistakes. You hear things like, we've been doing this for this many years, it must be true. I heard this from so-and-so person, that must be true. I took an SPE class, they taught this, so it must be true. And these kind of sentences are really obstacles to doing engineering. And so it's difficult, but I really challenge you as a listener to try to kind of take a step back, try to follow the data, the analysis, the logic, and again, empirical data that I'll show, rather than, and then somebody said so it must be true. Just a reminder, many brilliant scientists and engineers over the centuries have made, mistakes and have put out theories that turned out to be false. Albert Einstein and Linus Pauling are two examples. Linus Pauling is one of the greatest chemists in history, and he proposed that DNA is a triple helix, which of course it's not a triple helix, it's a double helix. So if these brilliant people can admit that they were wrong, then you and I can admit when we're wrong, and we have to let the data and the science lead us. And another way I think about this is really confirmation bias is an extraordinarily powerful force in our industry. When you're dealing with things that happen deep in the subsurface, you can't directly see them. And so we are, in fact, often having to infer things based on kind of indirect measurements or imperfect information. And that makes it very easy to believe whatever you want to believe. And I think what I believe very clearly happens a lot in our industry, and has certainly been taking place as far as I've seen in the DFIT stuff, was what I read in this nice article here. I read on Wired the other day. Never underestimate the power of confirmation bias. Confirmation bias means when you encounter information that disagrees with your pre-existing beliefs, you ignore that information or you find a way to rationalize it away. And when you find anything that seems to support your pre-existing beliefs, you shut down any kind of question about whether that's true and you accept it uncritically. And we're human beings. We all naturally experience this problem. But as an engineer, as a scientist, we have to work really hard to second guess ourselves, play devil's advocate, genuinely try to actively listen to alternative points of view, and ask yourself, is it possible that I have in fact missed something? And so I just really cannot emphasize this enough because in my work in this industry and working in DFIT, this is a huge problem, and it's an obstacle to progress very much of the time. So lastly, last point on this, I'm going to spend a fair amount of time in this presentation directly refuting the tangent method. You might say, well, Mark, why even talk about it? Why not just present your work and ignore the alternative perspective? Well, when I have conversations with people about DFIT, the number one obstacle is that they've internalized a lot of things that have been disproven. So they say, oh, that can't be true because of this or that. And this whole tangent method is a whole series of beliefs that kind of obstruct progress, because if you believe a series of things that are not true, then it kind of blocks you from being able to move forward. So what I'm going to actually do here is deconstruct some of the key fallacies that exist in the industry's theory and an approach in thinking about this. And I also want to mention that everything I'm going to present today is entirely consistent with what was done 20 years ago. So it was really perhaps from around 2000 to 2010, over that period of time when kind of a series of new DFIT ideas came out. And I'm largely going to criticize those and find problems with those. But prior to 2000, I think pretty much what was getting put out on fracture injection testing seems pretty valid. And we're trying to basically kind of move past some problematic concepts that came out in subsequent years. So this is not just about learning a new method and a new way of thinking about the problem, but unlearning and actually identifying and explicitly refuting problematic concepts, what they are and why they went wrong. And finally, I'll point out that even though the tangent method is declining in use, it's still the most widely used in the industry. There was a new SPE textbook that came out this year on hydraulic fracturing. It taught the tangent method. If you go take an SPE course on DFIT interpretation, it's going to teach the tangent method. And so this is a very deeply entrenched concept, and so we can't just ignore it. Otherwise, people will just continue to believe it. We really have to directly take it head on, explain exactly what's gone wrong and why. All right. So with that preamble finished, and sorry for that, but I felt it was necessary to explain. Let me go on with the presentation. So what is a DFIT? It is a form of fracture injection test. So specifically in a DFIT, you are going to be pumping fluid into the subsurface with the objective of creating a hydraulic fracture, and then you're going to shut in the well. You're going to allow that well's pressure to fall off naturally over time, and monitor that pressure and use the trends in the pressure in order to infer the stress, the permeability, and the pore pressure. Now, there's a variety of different terms for fracture injection test. Fracture injection test broadly meaning pumping water with the objective of creating a hydraulic fracture and then shutting into monitor pore pressure or bottom hole pressure over time. You'll see things like a mini frac test, a leakoff test, fracture calibration test, data frac. All of these terms actually have slightly nuanced different meanings, but what we find is very often they're kind of all muddled together. But generally speaking, a DFIT test refers to the idea that we're going to shut in for a pretty long time, like days or weeks. The well's already been completed, not hydraulically fractured, but in the sense it's completed that you maybe have cased in, cemented the casing, if that's how you're planning to complete the well, and so on. Also, DFITs, typically it implies that you're in a low permeability formation. Again, the terminology is inconsistent, but usually when we talk about a DFIT, we're thinking about shale. Why do we do this? Why don't we just do a well test? So what's a well test? A well test is you just inject water into the formation and you monitor pressure to estimate permeability. So why do we need to create a fracture? Well, number one, if we want to measure the stress, then we have to create a fracture, and a conventional well test isn't capable of doing that. But secondly, why not? What if we just want to know the permeability? Well, in very low permeability rock, you can't inject slowly enough to avoid hydraulic fracturing, right? If the permeability is 100 nanodarcies, you would have to inject very, very slowly to slowly create radial flow and do a kind of a conventional well test. So you basically have to create a hydraulic fracture. And so that's why we have to do a fracture test in low permeability rock in order to get the permeability. You might also ask, well, why do we need to do this to get pore pressure? Why don't we just drill the well and monitor pressure? And that's because it actually can take a really long time for the pore pressure in the wellbore to equilibrate with the pore pressure in the formation if the permeability is really low. So if you create a hydraulic fracture, you generate a whole bunch of fracture surface area that kind of can accelerate leakoff, and it allows you to more rapidly get out to the point where you can actually estimate pore pressure. So essentially, again, in a conventional formation, high permeability, you don't need to do a fracture injection test to get permeability and pore pressure. You can do conventional well testing. You would still need to do a fracture injection test to get stress. But in low permeability rock, you have to do a fracture injection test to get all three of these. All right, and this is roughly what it looks like when they pump a DFIT. Here, this is pressure versus time. This is I really should have labeled whether it's bottom hole pressure or wellhead pressure, but obviously in this case it looks like it's bottom hole pressure, very likely. Well, actually, no, not necessarily. Could be wellhead pressure. Completely depends. Anyhow, here they inject. This is prior to the formation of the hydraulic fracture. And so before the fracture forms, you're injecting much faster than the fluid can leak off. Now, if they're using something like a tow valve, that means that the wellbore is completely sealed, and then at a certain pressure or maybe at a certain time, the tow valve will open and fluid can rush out of the well. Alternatively, maybe the formation is already connected to the wellbore, but it takes kind of some excess pressure to build up and break down the formation. Breaking down the formation means when you first create the hydraulic fracture at the well. So either way, the fracture finally forms here, either because the valve opened or because the formation broke down. And then pressure drops off to kind of a stable pressure here that we might call the fracture propagation pressure. Then we shut in and we see pressure fall off gradually over time. So again, we can get stress, permeability, or pore pressure. Why do we want to know the minimum principal stress? Lots of reasons, and I've just listed off an incomplete list here. To use an exploration, very important for drilling to know the stress state, very important part of hydraulic fracture design, and it's also even used in reservoir engineering. For me, I do a lot of frac modeling, predicting the fracture geometry and production in response to different frac designs, we care about stress barriers. So here, fractures tend to grow in low stress regions, and they tend to avoid high stress regions. And so if we started pumping into this region, the fracture height might be confined here and here because of these stress barriers. Not necessarily, but it's possible, and this is something that could impact the design of the frac job. So this is just one of the many reasons that we need to know. Permeability is, of course, a fundamental input to reservoir engineering. As far as shale is concerned, we need to know it because in production in shale, if we look at a rate transient analysis plot like this one, we'll typically see a period of straight line. Now later we'll typically see the line curving upwards, but at least for a while we'll hopefully see a straight line. That straight line corresponds to linear flow. And the slope of this line is proportional to 1 over fracture surface area times the square root of permeability. And the problem here is there's a non-uniqueness. If the permeability is higher, we could match the data by assuming a lower area. If the permeability is lower, we can match the data by assuming a higher area. And so purely from looking at production data, we can't tell what the permeability is. We don't know if we have a lot of area and low permeability or small area and high permeability. So if we have a way of independently estimating permeability, then we can break this non-uniqueness. Now this is a really big deal. This is from a paper that we wrote at ATCE 2019 with this is Garrett Fowler, myself, and Craig Cipolla with Hess. And we looked at optimizing cluster spacing and well spacing in the Utica shale. Number one, what we showed is that we were able to history match the production data using very different permeability estimates. But if you use the wrong permeability to history match, and then you subsequently optimize well spacing or cluster spacing, you arrive at a very suboptimal solution. So just here looking at cluster spacing, you would end up spacing the clusters far too far apart, and you'd also end up putting the wells too close together if you think that the permeability is high, because that implies that the effective fracture length is low. So this is not just an academic exercise, but it's something that really directly impacts economic performance. And if you read the Wall Street Journal, you might see a lot of companies have struggled with well spacing. And certainly if you followed trends in frac designs over the past decade, you can see that there have been huge changes in cluster spacing. And I would argue that a major driver for the large changes that have occurred in cluster spacing and well spacing and the substantial amounts of capital wasted because of suboptimal designs have been due to inaccurate permeability estimates. You could also estimate permeability from core. Of course, that's a well-established technique. It works great in conventional rock, but you might consider a few details. Number one, that a shale is a pretty complicated rock, and when you bring it out of the ground, you change the stress, you change a lot of different conditions. That may not be a reliable estimate anymore because the rock has changed so much. Number two, there's different ways of estimating permeability from shale, and they seem to arrive at very different answers, and so that kind of should call into question the technique. And thirdly, you may not have a representative sample. So for example, in a DFIT, what we're doing is we're flowing reservoir fluid through the rock in the reservoir. So that means that if there's any pre-existing flaws and fractures contributing additional permeability on top of the intact rock matrix perm, that's going to be captured by a DFIT permeability interpretation. So this is a more direct way. Using a DFIT is a more direct way of getting a permeability estimate. It's more direct, it's in situ, it's more reliable than a core perm. And of course, my favorite is when people use RTA to estimate permeability. You might say, well, how do you estimate permeability from RTA? It's because they just guess the fracture length, right? And so that's not an estimate at all. It's just a guess. And so you really have to be very careful when people talk about permeability. Where did that come from? And you have to think really critically about, can we really trust that? And at least in this paper, we go through that there are, in fact, operators in the Utica shale who are using really high permeability estimates. And in this paper, we go through a variety of field data showing why that's not only inaccurate, but is a costly inaccuracy. Lastly, pore pressure estimation. Variety of different reasons why pore pressure matters. Number one, it is an input to a lot of different reservoir engineering calculations and reserves estimates and things like that. It can also help you with well spacing, because when you drill an infill well, you could perform a DFIT and you can see whether the pore pressure is depleted at that location. So here's just an example of some different wine rack completions going on in the Midland Basin. We can see how companies are spacing wells vertically and laterally. They're trying to figure out how many wells they can pack in to optimize their net present value to neither overcapitalize nor underproduce. All right. So what's the difference between a DFIT and a conventional well test? They both involved production or injection and then shut-in and monitoring pressure changes over time. They both involved using specialized plots to diagnose and quantitatively interpret formation properties. However, in a well test, you do not create a new fracture. In a DFIT, conversely, you create a new fracture and that crack mechanically opens, mechanically closes. That process of create a hydraulic fracture that opens and closes has no analog to conventional well testing, and it changes the physics and it changes the mathematics of how you would analyze the transient. And so this is a very important point, because if you're experienced in well test analysis, a lot of the plots look similar, a lot of the things look similar, but it can trick you, and you might take a concept or a method that you are used to using in well test analysis, and you might use it in a DFIT, and it might be right, or it might be really problematic and give you the wrong answer. And I'm going to give an example of that later. So it's very important to keep in mind. You've got to be very careful and understand that DFITs are a different beast. As a quick example, in classical well test analysis, you can do superposition of constant rate injection solution to predict the pressure response to a variable rate sequence. You cannot do that in a DFIT, and the reason why is because a superposition of those constant rate solutions assumes that the problem geometry is stationary over time, but of course in a DFIT, a crack forms over time, as well as the storage coefficient of the fracture well system is very large and changing over time, as is the conductivity of the fracture changing over time. And those introduce nonlinearities that violate the underlying assumptions of superposition when applied to a partial differential equation. So that's just an example of how you have to be very careful. Nevertheless, a basis in conventional well testing is very useful if you want to understand DFIT. And here I've listed off 4 of my favorite books on this topic. I used to teach well test when I was a professor at UT, and these are the books that I actually use. So I recommend these if you're interested. I also have one reference that I recommend above others on DFIT interpretation. This very wonderful book from 2000, Reservoir Stimulation, edited by Economides and Nolte. It remains, probably my favorite book on this subject. And Chapter 9 was written by Ken Nolte and Gul Rajani on DFIT, and it has a really nice presentation of the mathematics of the G function and how the kind of concepts of well test, or rather fracture injection test analysis were developed largely by Nolte and his colleagues. And so I really recommend this chapter. It's my favorite in terms of understanding the real theory of where things come from. All right, so that's the introduction. This next thing I'm going to talk about here is stress estimation, and specifically, as I alluded to earlier, these problems that have been identified in methods that are widely used. So this really underlies why we did a DFIT industry study in 2018. Prior to that study, I'd already done work at UTE with Sharma and Kramer and Hojung Jiang showing the problems with these widely used methods for estimating stress, which I'll call the tangent method or holistic method. Discuss them later. There are other problems. I'll mention some other kind of minor problems used and with methods used in practice. I'll mention at least one of those later. I won't go through all of them. And also some problematic permeability estimates in gas shale. So we were seeing that there were some issues, and but it's not enough to just identify problems, but really need to put forth a solution. So the idea of the industry study was actually to create not just hey, we're going to find problems and methods, but we're going to propose a method that can be used practically on real data by typical engineers without requiring any kind of specialized software. And that's our goal. And secondly, when you change the stress estimation method and you stop using the tangent method, it actually impacts other parts of the interpretation. And so we really need to make sure that we think through the full interpretation start to finish to make sure it all is internally consistent with the kind of the way that I'm going to present of understanding how a DFIT works. So that's what we did. And so some of the methods of that DFIT interpretation procedure are completely standard and normal. Some are completely diametrically different from the way things have been done the last decade or so in the industry, and some are kind of in the middle. All right. So first, this is going to be probably about a 20-minute discussion of how to estimate stress from a DFIT and problems with existing procedures. If you're interested in just seeing the step-by-step procedure and you want to skip over this kind of identifying issues with existing practices, feel free to skip ahead in the presentation. Okay, so Castillo 1987 did a nice paper summarizing what I would kind of consider to be the classical method of estimating stress from a fracture injection test, prior to the 2000s. This actually dates back much further to at least the 1950s. For example, Hameson and Fairhurst had a very nice paper there at the University of Minnesota in the 50s talking about how to use fracture injection tests to estimate stress. Those methods are still widely used in mining and geophysics. It's really just a petroleum engineering where we've kind of taken a left turn and do things differently from everybody else. And so that's what I'm going to talk about today. So the kind of classical method from Castillo 1987 was the following. On the top right here, we see a plot of pressure versus G function. And Castillo has labeled here that we should pick the fracture closure at the deviation from linearity on this plot. So right here, he would be estimating fracture closure right there. On the bottom right, he's made a plot of the derivative, dp dg versus time. And he said right here, there's kind of the flat line. It means the crack's open. And then something changed, so the fracture closed right here. All right. So I'm going to talk through mathematically where this came from. First off, it came from Ken Nolte's G function. So what is the G function? It is a function of time, and it's pretty similar to the square root of time. So you could think about the G function as just being a plot versus pressure versus the square root of time. It's a little bit more complicated than that. Nolte refined that and made it more accurate. The key property, and this is what really matters, this is what the G time is. If Carter leakoff is taking place, and I'll comment on that later, if Carter leakoff is taking place, then the G function is linearly proportional to the volume of fluid leaked off from the fracture after shutting. Okay, so if we go from G time of 0.5 to 1, that means that the amount of fluid that's leaked off from the fracture has doubled from here to here, and then it doubles from here to here. That's point 1. Point 2 is that prior to fracture closure, the fracture walls are freely opening and closing. And if the system is linear elastic, which it probably isn't completely linear elastic, but if it's approximately linear elastic, which is actually a pretty good assumption, then it should make a straight line because the fracture storage coefficient is linear as well as the leakoff with respect to G time is linear. So I'm going to show the equations for that later, but the point is they recognized when the fracture walls touch, something changes about the system, and that something must cause a deviation from the ideal conditions, creating this straight line. So that is the concept of Castillo 1987. This is essentially what would have been done universally in petroleum engineering up at least until the year 2000. This is also highly consistent with methods you would find taught in other fields. So for example, if you go to a book on rock mechanics, that's a famous textbook on rock mechanics. Here's Mark Zobac's famous reservoir geomechanics textbook. And here is a kind of sort of a standard mining engineering reference here talking about stress estimation. All of these references would still be teaching something consistent with what Castillo is teaching here in 1987. But if you went to an SPE course and took a class on DFIT interpretation, you would learn something different, which is a holistic method, and that's what I'm going to discuss now. So this is the holistic method. The key paper here is Bari et al. 2009. They also call it the holistic method. And here's how it deviates. Let me see here. So first, let's talk about the origin of it. It actually begins with something that's consistent with the Castillo method, but then it changes. So here's how it's consistent. If we look at the top left plot here, we look at this plot of pressure versus G time, and here's dpdg. We can see that at about this point, that's when dpdg stops being constant. And so actually this is the Castillo closure pick right here. So they have essentially, you can see here Castillo is identifying dpdg. When dpdg stops being constant, he picks closure. That is what they're showing here. And so what the tangent method relies on is a plot of G times dP dG. So here we have pressure, here we have the derivative of pressure, and here's where we take that derivative, we multiply it by G time again. You could get on a pencil and paper, you can quickly convince yourself that if pressure versus G time is a straight line, then dP dG is flat, and G times dP dG will be a straight line coming from the origin. And so if you do what the tangent method suggests in this case, which is to draw a line from the origin up this G times dP dG plot and identify the point where it deviates off the curve, that is a closure estimate. That is consistent with the Castillo method. But the other three plots here are showing something that is inconsistent with the Castillo method. And so that's where we take a big left turn. And I'll talk through how that happens. The first problem is that when you get into lower permeability rock, you typically see plots that look a lot more like this. So if you're in, 1 millidarcy and up, typically what you'll see is that dP/dG will be continuously decreasing or maybe flatten and then decreasing. But when you get into lower permeability rock, the most common signal is what you see here. And what we see here is that the following. First off, there's always an early time effect up here. We can ignore that. That's kind of some near wellbore effect. So we can always ignore this early rapid pressure drop. We'll talk more about that later too. Then pressure versus G time has settled into a straight line, and we can see here on this derivative curve, it's flat. But then what happens right here? The derivative increases. It's kind of hard to see because of the scale, but you can see here that this dP/dG, it starts to go up, and really the scale should be redone here. Visually, we can just look at the black line and we can see that it's bending downwards right here. So what they've labeled as changing compliance fracture closure. This is, in fact, right here, that's how Castillo would pick closure, right? And in fact, that's how I would advocate picking closure. The stress is roughly around right here. But the tangent method did something different. They said instead of picking closure at the deviation from the straight line like Castillo recommended, instead they're going to let this G times dP/dG curve keep evolving, and they're going to draw this tangent from here to the tangent of the curve, and they pick closure way out here. So it's always going to be later. You can see there's a pretty substantial pressure difference from here to here, and that's the difference. Now, how different they are is variable. Sometimes they're only a couple hundred PSI different, in which case you could probably say it's a rounding error. But sometimes they're 1,000 PSI different, in which case it's getting pretty substantial. And so that's the difference, and that's the problem here. Now, there's some other interpretations here. This fracture tip extension one here, this is sometimes we'll see a test where, it looks like G times dP/dG goes up forever. The whole test, weeks it could go up. And they actually will argue that the crack has not closed, because if we don't see G times dP/dG get to the peak, the crack's still open. So that's the tangent method, which I will describe some problems. So where did that come from, and why did they deviate from this method, which Castillo advocated and which is still used outside of petroleum engineering? Well, again, I think number one, it's because in shale, petroleum engineers started running DFITs in formations with really low permeability, and they started doing really long shut-ins. And that is kind of novel. I don't believe that if we look at mining, they're not typically doing that. They're not doing 1 week shut-ins in microfracs in mining very often. And so when you start doing these long shut-ins, you start getting these crazy looking transients, and it introduced some kind of new questions that needed to be addressed. Why does this curve do that, right? And Nolte wrote a really nice paper in 1991 doing some simulations, talking about what he called non-ideal processes. And I thought, largely speaking, what's in that paper is fairly reasonable. He proposed things like the following. Perhaps if the crack opens against different stresses, it might kind of gradually close, what they call height recession. If it takes a while for the crack tip to keep extending, then you might see some kind of early elevated pressure derivative like this and so on. So those ideas are not crazy, but then what's happened is they kind of just got turned into a dogma when these guys got involved. And we've started kind of making some really wild picks. Like you'll see people estimating fracture closure thousands of PSI, sometimes lower than it probably actually closed. And that creates all sorts of problems. So for example, fracture toughness describes how easily a hydraulic fracture can propagate through the formation. Laboratory experiments show that if the pressure is only a couple hundred PSI above Shmin, a crack should be able to propagate through the formation. yet we get these tangent method interpretations saying that the fracture propagation pressure was 1,000 or 2,000 psi greater than Shmin, and that's just hard to square with physical measurements of crack propagation. So that's the problem is this tangent. I can see what they were trying to do. They're trying to explain this data, and they had some kind of physical ideas behind it, but it's turned into a dogma, and it's led to some really big issues actually. So we'll talk through those. So there's at least two major problems with the tangent method. Number one, until the work that I did with my colleagues at UT, no one had actually run a complete numerical simulation of a DFIT from start to finish. Numerical modeling tools classically have, for fracture propagation, have not modeled closure, and they have not modeled post-closure. And so they didn't have a complete mathematical description of the closure process itself. I'll talk about that in a minute. And secondly, these methods are ignoring that the G function is derived assuming Carter leakoff. And Carter leakoff is an assumption about how fluid exits the fracture into the formation that is only valid if the fluid pressure in that fracture is constant over time. Of course, every single one of these plots shows that pressure is dropping a lot over time. That's what a DFIT is. And so if we assume that the pressure never changes and we do an interpretation based on that assumption, it's easy to see how that could lead to some erroneous results. So I'll talk about both of these problems. So as I mentioned, numerical simulators have assumed that when the fractures close, they have no aperture and leak off. So in a numerical simulation of hydraulic fracture propagation, conventionally, it's been assumed that the crack just kind of disappears. Not only is this a numerical solution, it's also an actually analytical solution. So and I'll mention this is never something that they actually say. You'll never, if you go to any of these references, they're not going to say, and then we assume that when the fracture closes, there's no fluid left in the crack. They just kind of do it. And then that's what kind of makes it tricky is you don't notice the assumption. But even going back to, for example, Nolte 1997 has a paper where he derives the linear flow time function. If you get into the fine print of that derivation, he assumes that at, quote, closure, there is no fluid left in the crack. And similarly, if you refer to like a Craig and Blassingame paper, they explicitly define the storage coefficient of the fracture before and after closure, and they actually are defining that the fracture, Craig and Blassingame allowed that there's a little bit of fluid in the crack, but they assume that the crack volume is constant, when in fact changing fracture volume is much more important than anything else. It's the dominant component of the system storage. So they've actually neglected the storage coefficient of the fracture opening and closing, even though that's the most important part of it. And so what's happened is these analytic solutions have done pre-closure solutions and post-closure solutions, and then they kind of just stitch them together. They've skipped over a solution of closure. And similarly, the numerical solutions have done that as well. The real problem here is that if you look at post-closure solutions, they assume infinite conductivity. So effectively what we find is a logical inconsistency that's been hidden by the use of two different analytic solutions. On the one hand, we do a solution for pre-closure that assumes when the fracture walls contact, there's no more aperture and leak-off happening. But then later on in the transient, that zero leak-off, zero conductivity fracture has turned into an infinite conductivity fracture. So it's a logical inconsistency that's avoided by just doing two different solutions. But what's really needed is a single unified solution to the full problem, which of course reveals that sort of inconsistency and also allows you to actually mathematically interrogate what should happen when the fracture walls contact. And so this is problem number one. So just first I want to actually talk about this because even presenting this work, I've sometimes gotten the feedback, well, of course fracture walls don't have any aperture after closure. One colleague said that, well, in shale, the grain size is tiny. It's less than a micron, and the residual aperture of a hydraulic fracture in shale is related to the grain size. Therefore, we know that it's incredibly small. So I've heard things like that many times when presenting this work, and so I'm going to present some alternative points of view and actually some data to show that that is not the case. So first, this is, again, to recap the point. The crack closes because the internal fluid pressure exceeds the normal stress that pushes in on the rock. Hydraulic fractures form perpendicular to the minimum principal stress. when they close, they don't just perfectly close like they're two mirrors just pressing together and there's nothing left. They have roughness, which is what I'm trying to illustrate with that. Here is examples of hydraulic fractures from core-through studies. So this is from the HFTS-1 study. This is a paper by Julia Gale. And these are real hydraulic fractures created from injection into the middle and basin. These are very rough features. These are not merely 1 micron of roughness, but it's millimeters rough. It's microscopic roughness. You could rub your finger on and feel it. And you can imagine, look at that ledge right there. If the crack was offset by even just a fraction of a millimeter, when that fracture tries to close, there's not going to be perfect closure onto that. And absolutely the fracture can be offset very slightly. So as the crack opens, yes, in a perfect mathematical idealized situation, it should close back perfectly. But of course, in reality, rock is heterogeneous. There are heterogeneities of rock properties, of stress. And so this sort of roughness is what is created by the heterogeneity and also causes fractures to not quite completely perfectly close back together. I mean, I would propose a simple experiment, go out and get a rock, smash it with a hammer, and then try to put the rock back together. And what you're going to see is it doesn't completely mesh back together. There is roughness when hydraulic fractured walls come back into contact. Here's an example from a laboratory experiment, Van Dam and De Potter. So they did opening mode hydraulic fracturing in this block of rock. Number one, they did in fact note that even at this very tiny scale, very small injection experiment, they observed the formation of these ridges and roughness features along the hydraulic fracture as it formed, which they interpreted as being caused by plastic deformation, mixed mode failure at the tip. And they said, quote, amplitude of roughness is much greater than grain size. And here's yet another example. This is from the In-situ experiment in the mid-90s. So they did a series of downhole experiments, field scale, in deep in the earth. And in this example, they put downhole tilt meters. They actually observed hydraulic fractures opening and closing. And in this test, what they're showing, sorry, it's a bad Xerox, is that after they did the fracturing test, about 20% of the maximum tilt remained permanently in place. And I would argue, I think not only I think they would argue, they were arguing that it's this sort of roughness, the fracture walls never perfectly came back together. So first, I don't think this should be controversial, but I can definitely tell you, giving talks at SPE workshops and conferences and having conversations, a lot of people have struggled to believe this. And so let's just, it requires reiteration that hydraulic fractures are not perfectly smooth. They have roughness and they do not close perfectly when they mate. That's very important to recognize. And I would also note again that the underlying assumption of a lot of classical analytic and numerical modeling on this topic have assumed that fractures don't have roughness and they close perfectly. And that's been a major source of challenge or problem or error in development of DFIT interpretation methods. So I like this paper. This is a particularly good one. Vogler, wonderful PhD thesis. This is some rock where they broke the rock, they put it back together, and they did flow experiments. You can see the roughness of this rock. This is a granitic rock. And they can show how, if, for example, it's a function of normal stress. So as they compress the rock more and more, the flow distribution changes. It does, in fact, seem to channelize through kind of channels created by the mismatching of the asperities. And so if we make a plot of average aperture versus stress, it'll look something like this. And there's a variety of, in fact, tons of papers in the literature from rock mechanics describing relationships like this. So in ResFrac, in the numerical modeling that I will show in this talk and in my papers, we don't try to literally represent every single little bit of roughness on a fracture. That's fantastic if you're doing work like Vogler's doing here. But if we're trying to do a field scale simulation, a large fracture, that's not going to be practical. So we talk about average aperture, and we assume that when the fracture walls contact, that occurs when the normal stress equals the pore pressure. There's a certain mean aperture equal to the size of the largest asperities, and then as the fluid pressure drops further, that aperture is squeezed down as the rock itself, the asperities themselves have the ability to deform. There may be also a slight kind of motion of the fracture and allow them to mate. And then there often would be an asymptotic kind of residual aperture. The one that I use in ResFrac is based on the Barton-Bandis hyperbolic law. Barton-Bandis and Bakhtar have papers from the mid-'80s where they did a huge number of experiments like this with all different types of rock and founded this hyperbolic law, represented the fracture-closure relationships across a very wide range of rock types. So this is a very well understood concept, at least in the rock mechanics community, and it's important for us to make sure that we communicate in the petroleum engineering community. All right, so that's point one. The second kind of problem that underlies a lot of the tangent method work is ignoring the effect of deviation from Carter leakoff. So I'll reiterate this again. I think it's a very important point. The G function is derived so that it is proportional to the volume of fluid leaked off after shut-in. And again, by the way, if you would like to see that derivation and read about that, refer you to Chapter 9, written by Nolte and Golrajani in the reservoir stimulation textbook. They have a really nice explanation of exactly where that comes from. It's probably clearer than the original Nolte papers. It's kind of written more of an educational style than some of its kind of SPE papers, so it's a really good reference. All right. But underlying that derivation is the assumption of Carter leakoff. So Carter leakoff assumes that at a particular location that the fluid leaked off is proportional to the square root of leakoff time. That is only valid if the fluid pressure in the fracture is constant. And as I've said, obviously the fluid pressure is dropping continuously during a DFIT. And so for a little while after shut-in, it hasn't dropped too much, and it's fine to approximate a leak-off as being Carter leak-off, and that's fine. So if we go back to references like this Castillo reference, for a little while we do understand that Carter leak-off is going to be pretty valid, so it's close enough to assume things are Carter leak-off. Although frankly, even here, I mean, there's been 600 psi of pressure drop. It is arguable that deviation from linearity could be related to that too. So it's even with Castillo, this was perhaps not being fully recognized like it should have been. But that's very important to recognize. Now, another clarification. I've given this as a presentation in the past, and someone said, oh, everybody knows about that. That's why we do PDL, pressure-dependent leak-off. Well, in fact, that is not what is actually done in frac simulators as PDL. So there's a term called pressure-dependent leak-off. Of course, leak-off is pressure-dependent, but when people use this term in petroleum engineering, what they actually mean is a pressure-dependent leak-off coefficient in the Carter leak-off model. So people have taken the Carter leak-off model and then made the coefficient out in front dependent on fluid pressure. That is not the same thing. It's not what I mean, which is if you actually just rigorously solve the flow equations for you don't get anything like Carter leak-off at all. So you can't merely make the Carter leak-off coefficient dependent on pressure and say, oh, we've handled pressure dependence. It's completely different. You can't use Carter leak-off at all in any form to model the full shut-in period. You have to do a more general mathematical solution. And that's not news, by the way. Of course, Mayerhofer wrote some great papers in the 90s talking about that and developing techniques around that. So this is not a new idea, obviously. But what I'm trying to emphasize is that this doesn't seem to be recognized when people apply tangent method interpretations of G-function plots. So, for example, if we look again at these G-function plots, let's think about what G times dPdG really means. If G is 0, so at shut-in, obviously this is 0. So G times dPdG always starts at the origin. Now at late time, remember you injected in shut-in. So at late time, dPdG has to go back to 0 because if you waited forever, everything would go back to normal and the pressure perturbation would spread out to infinity. So at late time, dPdG is 0. So you have something that starts at 0 and has to end at 0. So guess what it does between time 0 and infinity? It has to go up and then it has to go back down. That is true even if there isn't a fracture. Any injection test of any kind in any type of rock, with or without a fracture, if you inject and shut in, and then you make a G times dPdG plot, it will go up and then back down. And there will always be a, quote, tangent method pick, even if there's no fracture, right? And so that's something I think that's really important to keep in mind. And so what we see is people applying these G times dPdG plots really, really late out into the transient. Pressure has dropped thousands of psi. It's way past Carter leak-off. It's nothing like Carter leak-off, and they're still trying to do a G times dPdG interpretation. But really, whatever G times dPdG does, is meaningless with respect to the actual underlying mathematical theory and purpose for developing the plot, right? So the purpose of developing the plot is that we think there should be a straight line prior to closure because the walls are not in contact and the leakoff is controlled by Carter leakoff. If you go way out past that and now it's not Carter leakoff anymore, it's out the window, and who knows what G times Z P to G is supposed to look like. So, you'll see tests like this one. I've seen tests where G times Z P to G seem to go up for a week, and pressures drop thousands of PSI, and it hasn't closed yet. And then that just doesn't make sense because, again, you're basically applying a technique that was only designed for and is only valid for a period during Carter leakoff, and then you're applying it in this different situation that's not Carter leakoff, there's nothing to do with Carter leakoff. The method doesn't make sense to use anymore, but it's nevertheless people do use it. So this is another big problem I see happening. Here's an example of that in practice. This is a paper from Craig et al. 2017. This is the only paper I've ever seen where anyone ever actually tried to use data to empirically validate the tangent method. And so I'll talk a little more about that later, but in this example, it's a great one. This is a laboratory experiment where the shut-in pressure must have been up here around 30 megapascals or so. They know the actual horizontal stress because it's a laboratory experiment. It was 15. And they're attempting a G times dPg analysis here. So if the pressure goes from 30 to 15, that's not Carter leakoff. And that means it doesn't make sense to try to do a G function interpretation of that data set. It's just at its face, no matter what the trend is, it doesn't make sense. It's not valid. Yet that's exactly what they're trying to do here. So this is just an example of applying a technique developed for one situation to a situation where it doesn't apply and not recognizing that things have changed. I would also note, I also think this is kind of a good example of confirmation bias because this is a laboratory experiment. They knew that they were supposed to get 15. And so if you make a plot of G times ZP to G, it looks really weird in this laboratory experiment. And it looks weird because it's huge deviation from Carter leakoff is taking place. So it kind of goes up and then it's flat for the rest of the test. Well, again, I suspect that if you didn't know that the correct answer was 15, you might have picked closure here because that at least is in fact a tangent to the curve, or you might have drawn it out here and said, well, it never closed. I don't think if you didn't already know that the answer is supposed to be 15 that you would pick the tangent to the curve in the middle of this flat line. But that's what the authors have done. So they claimed that this was an experimental validation of the tangent method. And I think that's has two obvious problems. Number one is, again, this isn't actually the tangent to anything. And so I think it's just a confirmation bias where they've just sort of, maybe they saw a tiny little wiggle in the derivative right there and use that to justify making a pick near what was the correct answer. And secondly, the method obviously is not applicable to this data at all, and it doesn't even make sense to attempt this analysis. So it really does happen all the time. All right. So moving on, what's the solution past these problems? Well, the solution past these problems is to fully solve the problem without assumption, without these simplifications. So this is just a movie I'm going to show here. This is a ResFrac simulation. It's very similar to a simulation done with CFrac. And Sharma and his students, Hanyi Wang, have done similar types of calculations. It's all published out how to do stuff like this. And so there's two things that are neat about this simulation. First off, this is a fully numerical calculation of leakoff. So we're not using Carter leakoff. We're just solving the equations directly to get the right answer. Carter leakoff is sort of, under certain circumstances, is accurate, but often is not. So why do that? Why not just directly solve the governing and constitutive equations to get the correct answer? So that's what we did here. Secondly, when the fracture walls touch, we don't assume that the crack has zero aperture. We use a relationship that looks like this. When the fracture walls touch, there's a certain residual aperture, and then as the fluid pressure drops and effective normal stress goes up, that aperture squeezes shut more and more and more. If you do those two things, you can run a numerical simulation, and this is what the data looks like. Out here is near wellbore tortuosity, so we won't talk about that yet. I'll talk about that later. Here's where the walls come into contact. It causes the derivative to go up, and then it comes back down as the leak-off rate drops off. So this looks very much like a real DFIT that you might perform in shale. And this line is dPdG, the derivative of pressure with respect to G time. So this looks very much like real data. And in fact, it is a simulation that includes everything start to finish in the whole test. So these are the sorts of numerical simulations that I've used to develop the DFIT interpretation procedures that I'm going to show. The difference is we've overcome these kind of theoretical limitations and the use of methods that work sometimes but not in other contexts. We're just using a method that works, and it doesn't make those sort of simplifying assumptions. We can avoid these problems of accidentally making assumptions without realizing, and this is the basis of the method. Now, in this particular simulation, 8,300 is the minimum principal stress. It's about right there. Okay. So that's where we come to the so-called compliance method, which is outlined in this 2017 paper and then also in our URTeC paper. We have a derivation of this equation. It's a very useful equation. It says that the derivative of pressure with respect to G time is equal to the derivative of leakoff rate with respect to G time divided by the system storage coefficient. I think this equation is essentially what you would find in Nolte's old references going back many years. I don't know that I've ever seen him write it exactly like this, but I think this is a succinct way of summarizing Nolte's work describing this. So recall I explained that the G time is proportional to the cumulative volume of fluid leaked off after shutting. So since it's proportional to G time, if you take the derivative, dV dG, that's a constant. And similarly, the storage coefficient of the system prior to the contacting of the fracture walls is also a constant. And I'll actually pull up those equations here later in the presentation. And so the consequence is that the derivative is a constant. And so pressure versus G time is a straight line. This is the equation that underlies Nolte's original work on estimating leakoff coefficient from fracture calibration tests and the Castillo method. So this is not a new idea, although I think it's maybe very succinct and useful to write it just like we've written it here. And that's what's affecting this pressure transient. So I'm going to talk through this pressure transient. Again, this early time is a near wellbore effect, which I'll discuss later. But the key idea here is when the fracture walls touch, the system storage coefficient drops. And it drops because the system gets stiffer. I mean, you can just imagine if we come here as these, well, literally the slope of this line is changing. Aperture versus effective normal stress. But as the contact stress develops across that fracture, it's pushing back. It's getting harder and harder to close the fracture, of course. You can't interpenetrate the fracture wall, so, of course, the stiffness has to asymptotically approach infinity as effective normal stress goes to infinity. And so the system stiffens. If the system stiffens, storage coefficient goes down, and it's a simple mathematical identity to show that this derivative goes up. So pressure falls off faster, derivative goes up. That's where the fracture walls are contacted, and that is close to the minimum principal stress. It's maybe not exactly the same, and that's because there is some residual stress shadow caused by the roughness of the fracture, and that creates perhaps 100 psi of uncertainty in the stress estimate. But that's very different from what you might get from a tangent method estimation, which might be 500 or 1,000 psi lower in many cases. So that's where I'm headed with this. That's the underlying concept, and it's just based on a more complete description of the physics. Before I go to that, I'm going to talk about some direct empirical observations. So here's one. This is a paper that just came out this year. This is a series of DFITs or mini frac tests performed in wells drilled off a mining cavern, actually. So it's fairly deep in the earth. And they have a series of tilt meters or strain measurements from offset wells nearby. And so they performed a series of fracture injection tests. They can directly observe the fractures opening and closing. So this is displacement observed in offset wells versus pressure measured. And so you can see how this is before closure. There's a linear relationship between pressure and deformation. Then here's where the walls start to touch. We can see that there is about, let's say, 1.5 megapascal, which is a couple hundred psi, where it's sort of bending, and then finally it's really crunching down here. So they can compare these sorts of measurements to things like the tangent method. And so, for example, the bottom left here, I'm trying to remember which of these is which. I believe what they're showing is that the actual physically measured stress here was about 5 megapascals in this experiment, but the tangent method just shows G times dPdG going up continuously. Would say the fracture never closed even once it got down to 3. So if you go through this paper over and over and over, what they show, like what they're showing here is, again, the actual physically measured fracture closure from the strain measurements and the tilt was around here, but the tangent method is coming in far lower. Every example in this paper, they have a bunch of tests, shows the same thing, that this bar rate tangent method is coming in way lower. And now we can, what I've just discussed can kind of help explain some of the reasons why. Number one, when pressure goes from sub-in to 2 megapascals, there's nothing to do with Carter leakoff anymore. All right, and so again, the underlying concept that Castillo started with is completely out the window, and there's no reason to even be using a G-function analysis out here at 2 megapascals. And so basically the position of this peak, which is with the bar rate tangent method as peak and closure, has no relationship to closure at all. It's just, in fact, if you're interested in what it does represent, I have a paper from 2017. It's called the spurious deflection on the superposition log-log linear time plot or something like that. Goes through some math to show that the peak in G times dp to G is actually caused by the late time transition into something called impulse flow. So it has to do with the pore pressure and the leak off, and has really nothing to do with closure. So anyway, this is example number one. Very nice direct physical in situ measurements showing that the tangent method is consistently coming in with large inaccuracy. Second example, we use those IMSITE tilt meter experiments. This is a figure that was actually published in the Economides and URTeC textbook showing tilt from the offset wells versus pressure. And we can see pretty clearly that right here, this is the pressure at which the derivative of tilt with respect to pressure changed pretty abruptly. And then if we look at the shut-in transient and we try to apply the tangent method, we find that the tangent method is predicting that the closure stress should be somewhere down here, which of course it is not. A third example is microfrac tests, and we can look at the reopening pressure. So it's a little bit of discussion here, but first, one problem we have is that near wellbore tortuosity in horizontal wells is substantial, and so that means that the reopening pressure and the fracture propagation pressure when we do a fracture injection test in horizontal wells is not reliable. So actually, I'll just go back here, and we can see here in this URTeC shale example, the actual pressure at shut-in was like 11,500, maybe 12,000 psi. Very quickly dropped off down here to closer to 8,300 or so. We don't think that this we think this is near wellbore tortuosity. I'll talk about that later. But in a microfrac test, and that's related to the fact that this is a horizontal well. In a microfrac test, this is a vertical well, open hole, and they just inject a little bit of fluid, in this case from wireline tool, into the formation. So there's no near wellbore tortuosity. It's a vertical well. The fracture is going to be vertical, and it's going to form directly off the well. So we can compare the reopening pressures. And a reopening pressure means in the second injection cycle, when they start injecting into the fracture, at what point does a lot of fluid start to go into that fracture? And that's the point where pressure rolls over, and that has to occur when the crack reopens. Crack reopens because pressure exceeds the minimum principal stress, right? So just from just investigation of the reopening pressure, we can see that the reopening pressures are very close to the ISIPs. And again, if you gave this to somebody from mining sciences or somebody from a geophysical community or anybody from petroleum engineering prior to maybe the year 2000, anybody would agree that the stress estimate should be up here around 50 psi or so. Yet this author is showing that what they've done is they've made this G times dp dg plot. They've looked for this tangent here. So they've drawn this straight line. Here we can see G times dp to G in this data is curving downwards. And they've picked this tangent. And these red dots are showing the tangent method closure pick. And I think it's just obvious on its face that this is not the correct closure pick, right? If this was in fact the minimum principal stress, then we would see the fracture reopening right here. We would see the fracture kink over. There would be this, apparent change in the ability for fluid to flow into that fracture. It's just not there. It's just clearly refuted by the data. And so this is another nice example. And I would say generally, when microfrac tests like this are performed, you always see this. You will always see, in microfrac tests, I think always is a strong term, but the great majority of the time you ought to expect that the reopening pressure is going to be up here near the ISIP, and if you try to apply a tangent method type interpretation, you're going to get a much lower pressure that's clearly inconsistent with the data. And I want to make that even clearer here. because I really want to look at that reopening response. So if let's take, for example, the tangent interpretation. They're estimating that stress is here. And then you might say, well, if stress is there, why did pressure have to get up here in order to propagate the fracture? And so they would argue, I think the way that Barre would probably argue it is something called a process zone stress. They'd say, oh, well, you need an extra 500 psi of pressure to propagate the fracture. So you have a crack that should reopen at this pressure, but propagate at this pressure. So if the fracture reopened, if this was the stress, certainly the fracture should reopen at the stress. But if it took 500 extra psi to propagate, this is what it would look like. So I ran a numerical simulation where I made the fracture toughness really, really high. So it's really, really hard to propagate the fracture, and you need a bunch of extra pressure to get the crack to propagate. So what happens is when you re-inject, you inject back into the fracture. When the pore pressure reaches SH-min, the crack reopens, and so you see a kinking in this pressure versus time plot. It kinks because the crack is reopened, and now fluid's able to fill up that crack. The storage coefficient of the system has changed. And then finally, when you get to the fracture propagation pressure caused by the high toughness, it would flatten out. So this is what the reopening response should look like if the tangent interpretation is correct. But obviously that's not what it looks like. In fact, what it looks like is pressure just blows past that. The system doesn't even notice that it's past 4873 psi, and then there's a sharp change up here at the ISIP. So this is what it would look like if you have a kind of normal toughness. And by normal toughness, I mean the fracture toughness that you would measure in a laboratory, a physical measurement. And if that's what it looked like, then you would see that the crack should reopen and then kind of flatten out around SH-min. So that is in fact what the data really looks like. So this is why it doesn't make sense to say, oh, we have these huge fracture propagation pressures, because if we did, the crack should still reopen at the lower pressures and then propagate at a different pressure. It would create a kink. I have personally never seen that in data. I want to just give one more example of confirmation bias. You really have to be careful with this. Again, back to this Craig et al. 2017 paper. They actually went back to this data, and they tried to argue that this data supported the tangent position. So how did they do that? Here is a plot of what they're showing here on this green is the tilt meter response, and then this is time. Okay, so we can see that tilt is flat, and then about right here it starts to lift off, being flat, and then right here it abruptly turns left. Okay, so if I just showed you that green curve, you might say, well, what are the notable points on this curve? Well, you might say that's a pretty big change. And then secondly, you might, if you really were looking for notable points, you might say, well, about right here is where the flat line started to bend, right? Well, if we reanalyze the shut-in transient, the fracture compliance method predicts that this is the stress, should be the reopening pressure, and the tangent method will predict that this should be the reopening pressure. So if I looked at that plot, I would say, well, the tangent method found a spot in the middle of a straight line, yet the fracture compliance method seems to have estimated stress exactly where the tilt suddenly veered off to the left and dramatically changed. I would take this as a validation of the fracture compliance method and a pretty clear refutation of the tangent method, which is basically picking a pressure that's right in the middle of nothing. Yet amazingly, these authors claimed that this data right here is supporting their interpretation, that they think that the green line shows that this is the fracture reopening pressure. So I would offer that this is simply confirmation bias. It allows these authors to identify a reopening pressure in the middle of a straight line. This paper had other problems, and sorry to harp on it, but I think it's quite influential. It's actually been downloaded more times on OnePetro than the URTeC paper. So it's had a substantial impact on the industry. Another problem with this paper is they claim to have done a blind test to laboratory data and claimed that they were able to correctly predict SH-min, but it turns out that in fact they did multiple blind tests to different laboratory experiments, and they only divulged the existence of one of those laboratory tests. So that again just sort of should underlie the technical and methodological problems that underlie some of the claims that are made around the tangent method. Going to mention one other kind of minor error. There's actually several, but I don't want to harp on all of them. They're mentioned in the URTeC paper, but I just want to mention this in particular. So one method that's sometimes used in the industry is people try to estimate fracture size based on the timing of the onset of late time linear flow. And so here is an excerpt from a paper from 2002 where they, as they say, borrowing from conventional well testing, the dimensionless time function can be used to estimate the time to pseudolinear flow. Well, in conventional well testing, this equation is valid and should be used. The problem is they've taken the equation for the transition from bilinear flow to linear flow in a conventional well test and applied it to a DFIT. And it is not applicable to a DFIT. It is an equation derived for a completely different physical problem, different context. What we found is it doesn't even qualitatively capture the relationship. So for example, if we had a higher modulus, that would imply that the fracture should be longer and skinnier. And in reality, what we've shown with modeling is that if the fracture gets larger, but you inject the same amount of water, then leakoff will happen faster and the fracture will close sooner and you would get late time impulse sooner. But what this equation implies is the exact opposite, that if the fracture got bigger, it would cause late time impulse to occur later. So not only is this derived from a different physical context and it's not accurate, it's not even directionally accurate. So this is an example of how if you just take an equation from conventional well testing and just plop it into DFIT, you can arrive at erroneous conclusions. And so you have to be very careful. And again, you have to be careful because this is a method that is taught and used in the industry. Okay, so I believe I am, still a little more on the compliance stuff. Just want to compare. So here I have this, this is this URTeC DFIT. And here I have a G times dPdG plot, and here I have a dPdG plot. So the compliance method is to identify the point where the derivative dPdG reaches a minimum, come up about 75 psi from that roughly, and that's where we think the fracture is closed. There is a little bit of imprecision in the exact location of closure, but it's about right here. Versus the tangent method, if we took that same data, we took the G times dPdG plot, we take this tangent up here, we would arrive at 76,300. So the difference in these two estimates is, maybe 500 psi. Oh, here we go. So it's just about 500 psi. So if you divided 500 by 8,000, you might say, well, it's not that big of an error. It's only a few percent, 4% or something. But let's consider the estimate of net pressure. So net pressure is the difference in pressure minus Shmin, and that's what determines fracture aperture and fracture size. So again, I'll talk about the near wellbore tortuosity in a minute, but our best estimate for fluid pressure in the fracture after shut-in is maybe 8,400. So if we compare that net pressure estimate, 8,400 minus 8,025, versus 8,400 minus 7,600, that's about a factor of 2 difference on net pressure. So whereas the stress estimate in an absolute basis may be 4 or 5% different, what you can see is that when you get into things like net pressure, you could see 100%, 200, 300, 400% difference in the estimates. And these imply very different fracture geometries. And the estimation of fracture geometry gets fed into things like the permeability estimate and fracture modeling. And so it impacts all these things. So even though we're only talking about 500 PSI, that 500 PSI makes a big difference. Okay, so that is it for the discussion of the tangent method. So I'm now going to move on finally to talking about the step-by-step interpretation procedure that we developed in our URTeC paper. Roughly like this: you're going to construct plots, you're going to estimate stress, you're going to identify flow trends, estimate pore pressure, estimate permeability, and there are some additional supporting plots. I actually am not going to go through this full procedure. Please refer to the paper. It goes through all the details. Also in the paper, I have a detailed derivations of everything, which most readers won't be interested in, but some readers may find interesting. So I'm going to do a worked example. I'm going to use a Utica Point Pleasant gas shale DFIT. The overall setting is described in this paper by Sapola, 2018. And again, this is further discussed in the URTeC paper and another follow-up paper at ATCE the following year. This is the same step-by-step procedure that's given in section 2.2 from the URTeC paper. All right, first off, we recommend using plots of pressure and dPdG versus G, not G times dPdG. What we found is that the way that we're interpreting the data, it's better and more clear to use just the primary derivative. So just to recap here, we don't use these G times dPdG curves. Basically, don't use it for anything. We use these dPdG curves. All right, So I think I've alluded to this several times, but why does this curve have this kind of S shape? So the derivative starts high, goes down, goes back up, goes back down. And this is what probably 2/3 to 3/4 of DFITs look like. They're not always this clear. I'd say probably only maybe a third of DFITs in shale have such a clear separation between the minimum and maximum DPDG. Sometimes it's a little smoother. In fact, I think I have an example way later. Let me try to find it. It could be way later. Let's see. Yeah, this is another example where clearly the minimum and maximum of DPDG, it's not so clear, but it's still there. And what I've come along to in my work is that if I see this DPDG come out and it inflects up, even if it doesn't quite hit a maximum, if it's clearly inflecting and making this S, then I'll continue to do the interpretation. If I don't see a clear separation, I might label it as being a weaker indication of closure. I might call it an adequate confidence instead of high confidence. Now, in roughly a quarter to a third of DFITs in shale, we won't even see that. We'll see the derivative just completely decreasing the whole time. And I'm going to discuss that later. It's an important topic. We also see that in high permeability rock, and we also tend to see that in microfrac tests. So it's something that's certainly common, and it's important for us to discuss. But for now, I'm going to talk about this kind of main path, most common thing, which is this S-shaped DPDG. So here it is. So I'm going to talk through every wiggle and what causes those wiggles. The first one is near wellbore tortuosity. So you're in a horizontal well, and you're probably trying to initiate out of perfs, maybe open hole, but these days typically perfs, and there creates a pinch point. So fluid gets out of the perfs. It may actually open up a microannulus. It might create an axial fracture along the top and bottom of the wellbore, and it's going to form longitudinally along the crack, along the well. The problem is the well's drilled in the direction of Shmin typically, or close to that direction most of the time. And so the crack wants to be perpendicular to the well, transverse to the well. And so you need to get a 90-degree rotation as this longitudinal crack goes 90 degrees and rotates into being a transverse crack. That is a complicated process. Fractures don't like rotating through solid rock. And so here's some nice illustrations from a couple different papers discussing this topic, this Bazan and Meyer paper and this Kramer paper. Of course, Kramer is actually showing a picture from a Warpinski 1983 paper. And so people are discussing how this sort of pinch point can develop. And so in this data here, the shut-in pressure is 11,500, but the interpretation is that the pressure in the fracture at shut-in is just 8330. So there's a huge pressure difference between the fracture and the well created by this pinch point, created by this tortuous fracture flow pathway. Now that pressure difference dissipates pretty quickly, right? So the pressure gradient across something, across a resistor, across an obstruction, proportional to flow rate. When you shut in, there is still wellbore storage. So the fluid in the wellbore has some compressibility, and it's maybe a 350 barrel wellbore and 3,000 psi of pressure difference in a 350 barrel wellbore. Even if it's full of water, which is pretty incompressible, that still could be a couple barrels of fluid that's released from wellbore storage after shut-in. So you might have a couple barrels of water flowing into the fracture after shut-in. And that's why it takes a little while for this pressure gradient to dissipate. But over time, that pressure gradient is going down, the flow rate's going down. And so after tens of minutes, hopefully, the pressure you're measuring in the well is now close to the pressure in the fracture. Now, in a worst case, that pinch point could theoretically totally seal off the connection from the far field fracture to the well. And if it did, then you're toast. You can't measure anything. So you should be paranoid about that. And if you get weird measurements, that could be the cause. If that happens, what I think could be, you might see is the pressure could like flatten out to a really low derivative and then just stay really flat and high for a really long time. If that happens, maybe there really truly was a total seal off. But that's not most cases. Most cases, this dissipates. And so when we get out to about this part of the transient, we're as close to ideal. We're as close to the Nolte-Castillo optimal situation as possible. There's no longer near wellbore tortuosity. The fracture walls are still out of contact. And so we get this straight line that we're supposed to get. And then we get a deviation from linearity when the fracture walls come into contact, just exactly like Castillo is saying. So that's called the compliance method of picking fracture closure. Skip past the early time data, and when the pressure derivative goes up, that's a compliance method closure pick. If you want, you could just call it the Castillo method because it's exactly the same method. That causes derivative to go up. And then what happens here is we start to get deviation from linearity. So let's remember that this G function plot, we're only supposed to get a straight line if it's Carter leakoff and it's an open crack. So as we get deviation from Carter leakoff is happening more slowly than you might have expected because pressure has been falling off, so you have less driving delta P. That causes the leakoff rate to drop off, and so late time dPdG goes to 0. So that's why you get an S. Near wellbore tortuosity, ideal behavior preclosure, contacting a fracture wall stiffens the system, and then deviation from Carter leakoff slows down leakoff. That's every bend in this curve. The after flow rate actually looks quite a bit like a square root plot. That is what I read in a textbook from Wright, 2000. That's in the Economides multi-textbook. And when we did the DFIT study, we looked at a whole bunch of field data, and we developed a way to estimate the after flow rate. We made plots of delta P versus after flow rate, and in fact, it does look like a square root curve. So that textbook equation seemed to work very well in the shale DFITs we investigated. We also need to estimate what do we think the pressure in the fracture was actually at shut-in. That's useful for purposes of doing calculations to estimate things like net pressure and permeability. And so what we're recommending doing is to identify that point of minimum dPdG and then draw a tangent to pressure, extrapolate that back to the y-intercept. The idea being that in the fracture itself, this system has been ideal the whole time, and what we're actually measuring is being impacted by the near wellbore tortuosity. So we assume that this ideal trend probably existed roughly back to shut-in, and that's where we get what I'm calling the effective ISIP. So in the terminology that we use in the URTeC paper, the literal ISIP is the actual ISIP measured in the wellbore. The effective ISIP is what we think that the initial shut-in pressure was in the far field fracture. Not everybody uses the same terminology as this, so just be aware. But this is the terminology that we put forth. And the effective ISIP is the estimate for the fluid pressure in the fracture at shut-in versus the literal ISIP, which is the fluid pressure actually measured at shut-in the wellbore. All right, so I've talked about this quite a bit. This ideal part of the DFIT when we get this, pretty straight line on pressure versus G time. I talked about this this chain rule decomposition derivation, showing that the derivative is the leakoff rate with respect to G time divided by the storage coefficient. So here I'm actually going to make this more explicit. And again, going back to the Nolte papers, you can find this equation. The volume of fluid leaked off after shut-in is a bunch of stuff times G time. So that's what I meant when I said that the volume of fluid leaked off is linearly proportional to G time. And this is leak off after shut-in. So here we have a leak-off coefficient, area. This is the duration of injection. So if we took the derivative of this equation, well, the G time just goes away. So dPdG is a constant, and that's very powerful. This is really the essence of Nolte's innovation. Then we can look at the system storage coefficient. There's two sources of storage. One is the wellbore storage, which is the compressibility of the fluid in the wellbore, and then the second is the fact that the fracture itself is opening and closing and its volume is changing. And you can quickly do some back of the envelope calculations, which we do in the paper, to show that that's the dominant component. There's a nice paper here looking at pump and flowback tests and discussing how this changing fracture compliance, I don't know how to pronounce this fellow's name, Rain or something. He is showing how the changing fracture compliance is affecting the flowback test. Same concept, we're just applying it to a pump-in shut-in test and putting it in the context of a G-function plot. This is the dominant term until the pressure has gotten way below SHmin. So some simple back-of-the-envelope calculations can show that maybe once pressure has dropped thousands of psi below SHmin, finally this term becomes negligible and the storage coefficients, or the wellbore storage coefficients dominant. So this is what it is. So prior to closure, SF is constant. Once the walls contact, SF starts to go up, this starts to go down, and then that starts to go up. So that's how it works together. So the beauty is that we've now written equations for storage coefficient, and we've written an equation for dVdG. This is from Nolte. This is from our understanding of the system storage. And so when we plug those equations into this derivative, we can get this equation now. The derivative is equal to this number right here. Note that I've dropped out the compressibility of the fluid in the fracture because it creates a nonlinearity and it's very small. So we can neglect that very safely in any practical case, or probably almost any practical case. Maybe not a mini frac test or a very small microfrac test. So this is a useful equation, and this equation actually is the essential aspect of Nolte's work on establishing leakoff coefficient from a G function plot. The reason that his derivation is so useful is because it's possible to write an equation like this. We can measure dPdG from field data. We can estimate these other parameters, and we can then infer the leakoff coefficient. All right, so that in fact is done already in the literature, but we've extended them a little bit. So a paper that I found very interesting and influential in our work is this Valko and Economides 1999 paper. It's also been, this method's been used a lot in more recent papers by Christine Economides and her graduate students. Really liked this approach because what they've done is they've taken, they bring in mass balance. So they write a mass balance equation, and they show practically how you can use this type of equation to infer the fracture size, the leakoff coefficient, from the preclosure data. And they actually explicitly in these tables here give the equations to use. So these are very useful, but there are two ways that we've extended these equations a little bit further. Number one, wellbore storage is not used in these equations. So these are all valid if there's no wellbore storage, which again, if you do like a 10 barrel DFIT, wellbore storage could consume 25% of the injected fluid, and so it's not negligible in small volume DFITs. And secondly, they have this equation here: fracture extent from intercept assuming no spur loss. I find this to be confusing. These equations are actually only valid estimates of fracture size if there has been zero leak-off during injection. So it says no spurt loss. That seems confusing to me. It should say assuming no leak-off during injection at all. And again, that's not necessarily valid. So we followed the same approach as Valko and Economides, but we've just done these two things. We've modified these equations in Table 3 to consider the effective fluid leak-off during injection. And here, these equations in Table 2, we've modified to include the wellbore storage coefficient, which is what we can see right here. So what we find is we can, again, write down this derivative equation here. And so this is the derivative as a function of things like the fracture stiffness and leak-off coefficient. We can write that for a PKN fracture or a radial fracture. And then also we can write down a mass balance equation considering wellbore storage, fracture storage, and leak-off. And what we find here is two equations and two unknowns. The unknown number 1 is leak-off coefficient, and the leak-off number 2 is the fracture size, which impacts the stiffness of the fracture preclosure. And so this is two equations, two unknowns. They can be solved, and they can be used to estimate both simultaneously. So it's a preclosure estimate of the leak-off coefficient. Now, the leak-off coefficient can be related to permeability. And what we found is that when we compared preclosure and post-closure permeability estimates, they were quite consistent. Typically, the preclosure permeability estimate from these leak-off coefficients is about 2 times, maybe 3 times higher, but they're consistently different. And so within a reasonable error bound, which we have to consider that certainly all of these estimates of permeability are fairly uncertain. They have considerable error, but at least it's getting us in the ballpark. So this is a method that we developed, extending Valko and Economides to include these new effects. Basically based on this chain rule decomposition and then plugging in the derivations of storage coefficient and leak-off volume from Nolte's derivations, and then combining with a mass balance equation. Of course, once the fracture walls come into contact, the contacting of the fracture walls impacts the stiffness term here. So this is an equation that's valid specifically prior to the contacting of the fracture walls. So dPdG, we pick that here from the minimum. This is prior to closure. And if we take that point prior to closure, then this equation is valid. There's another issue here. Remember, I've already talked at length about how the G function plot assumes Carter leakoff, and we know that in fact there is deviation from Carter leakoff. So this is a concept that's been known for a long time. Mayerhofer and Economides, and these Mayerhofer, I think Economides as well, they developed these equations for estimating permeability that account for the deviation from cardial leakoff. And they're using here a convolution integral of a constant rate solution. So that is absolutely a valid extension, and they are even able to do things like estimate filter cake permeability, which is important but not relevant to DFITs because we don't pump filter cake forming fluids. But if we go to these original papers, the challenge there is they don't provide a way of estimating fracture surface area in the way that Valko and Economides do. They actually are recommending, you need to go use a frac simulator to predict fracture surface area, iterate back and forth, and it's not a kind of fast and easy approach. It requires kind of iteration with a frac simulator. So what we did is we combined this approach here from the Mayerhofer approach with our extension to the Valko and Economides approach. So we're going to use a mass balance, but we're going to replace this equation with a more general expression that accounts for changing pressure over time. One other change we're making is that Valko and Economides did a time convolution integral of a constant rate solution, but that requires you to know the leakoff rate, which you actually do not know. And so they have to approximate the leakoff rate. And so we do it more directly. We do a time convolution integral of a constant pressure solution because we do actually directly measure pressure. So we don't have to do an extra step. So we can write here, this is an expression for the cumulative volume of fluid leaked off. This particular equation is for since the beginning of injection, where we do a time convolution integral of the pressure measurements. We have to account for near wellbore tortuosity in this calculation. And then we can actually write this equation directly. And we define a function called the H function, and it's selectively named. It's like the G function in that it's proportional to volume of fluid leaked off, but it is proportional to volume of fluid leaked off considering any general history of pressure, unlike the G function, which assumes a constant pressure with time. And the nice thing about the H function is it can be derived solely from measurements of pressure and also an estimate of the bottom hole pressure. And that makes it a useful kind of analytic tool. Once you have it, then you can just define it as a variable and use it around in equations very easily. You don't have to carry around these big integrals all the time. So what we do, we write this mass balance equation just like we did here, similar to the Valko and Economides approach, including wellbore storage, including leak off during shut-in, but we swap out the G function for the H function. We have a more general and more realistic estimation of fracture of leak off, accounting for changing pressure over time. So what we're trying to do here is basically combine all the best features of the Mayerhofer method and the Valko Economides method, plus adding in our use of the wellbore storage, the use of leak off during injection to calculate fracture size, and we're using this H function to kind of simplify some of the math. So in my view, this is the most robust method that we have available. It integrates pressure response rather than depending on a single point estimate of derivative. It accounts for changing pressure over time. It really accounts for all the key processes. So this is the method that we like to use the most, actually. We use this method, and this is the one that I recommend. It's a little bit harder to do practically because you have to perform a convolution integral. That can be done in Excel, but it's a little bit clunky. It's a lot easier to do with a computer program, whereas this G function method is very easy to do in Excel. But typically the G function and H function methods that we're showing here are pretty similar. They don't usually show big deviations, but occasionally I think that this G function method can be vulnerable, like since it's relying on a single point estimate of dp/dg, I think it's a little bit less robust sometimes, and so G function is my preferred and recommended method. Again, when we've compared, this is a pre-closure estimate to get permeability, and when we've compared these permeability estimates to post-closure permeability estimates, they're usually 2 or 3 times higher. And so just keep that in mind, that if you have a post-closure permeability estimate possible, you don't need to worry about this H function method. But very, very often, transients don't ever reach, they're not shut in for long enough to reach late time. You don't have post-closure permeability estimates available, then this H function method is a substitute. Instead of using post-closure, you can use this H function pre-closure method to get a good permeability estimate, divide by 2, and now you actually have a robust permeability estimate. So that's the main thing here, is you can get a permeability estimate from a shorter shut-in. It's going to be consistent with what you would have gotten from a much longer shut-in, and it's a very robust method that accounts for all the relevant and key things. All right. Next, we could also look at perhaps how this deviation from Carter leakoff affects the estimation of stress itself. So again, note that we've been relying on this deviation from dPdG to pick closure, but that's assuming that we still have Carter leakoff. So what if we're in a system where there's a lot of Carter leakoff happening, or sorry, the deviation from Carter leakoff is happening simultaneous with closure? I'll refer back to this paper here. Which paper? Way back here, this paper. So this paper here, where because it's a laboratory experiment, it's a rather unusual situation. Pressure has dropped off dramatically by the time that the fracture is reaching Shmin, the normal stress on the fracture. And so there's a ton of deviation from Carter leakoff. So this is a situation where I said you can't use a G-function analysis. So what should you do? And here's the solution to that problem. So we can deconvolve the effect of changing pressure on leakoff rate to estimate system stiffness as a function of pressure. So essentially, instead of using Carter leakoff, we're using the DH function, and that allows us to kind of account for this changing pressure over time and how that impacts leakoff rate, and so we can still infer this changing system stiffness over time. And what's really neat is that the H function makes this analytic derivative or development very simple. So we can write here that the derivative of pressure with respect to time, we can do a chain rule decomposition. We can show how the derivative of volume with respect to time is proportional to the derivative of H function with respect to time. Do a little bit more of analytic analysis, and what we can find is that we can generate this plot of relative system stiffness versus pressure, and all we need to know is pressure itself, the pressure measurements versus time, as well as we do need to have an estimate for the pore pressure. So that's kind of cool. You don't have to do any more analysis than that, and you can generate this plot. Now it's called relative system stiffness because the y-axis here is proportional to the system stiffness, but is not explicitly a measurement of the system stiffness. And so when we compare in this URTeC case, this is where dPdG goes up, and that's the kink here we see where the relative system stiffness suddenly starts to go up a lot. Now it's not always this clear. I wish it was. Sometimes this is a little bit curving, and there is some subjectivity in trying to estimate when exactly do we think is the right stress estimate. But keep in mind that if we were using the tangent method, we would be somewhere like way up here, when the system appears to have gotten at least 10 times less stiff. We also want to refer the listener to Wang and Sharma, 2018. They have a very similar approach here, where they also do a deconvolution of the pressure measurements to estimate. What they actually do is just directly estimate system stiffness. I think also they're kind of doing something kind of along the lines of combining with a mass balance equation. So anyway, I just want to refer the reader to that. That's another important reference on deconvolving changing pressure versus time to estimate the system stiffness changes over time. All right. Now, what about this DFIT? This is a tricky DFIT. This is from the Bakken, and the red line is dPdG, pretty much going down the whole time. I argued again, I showed this example where this is from the Upper Eagleford, dPdG, there wasn't like a great separation, but sometimes there's just nothing, right? So how do we explain this? And I'm going to give a little bit of an unsatisfying answer because there's several possible explanations. But the easiest explanation, and I think the most important one, is rapid closure. And so here I'm going to show some examples. Here is a simulation that was performed in ResFrac where we created a hydraulic fracture, and then the fracture is intersecting some really conductive natural fractures. So even though the matrix permeability is pretty low in this simulation, the effective system perm is high. It's order of at least tens of microdarcies, if not higher. So when we shut in, the fluid in that hydraulic fracture very rapidly leaks off into these conductive natural fractures. And what happens is a plot of dPdG is pretty much just monotonically going down. There's a little bit of numerical wiggle there, but basically going down continuously the whole time. Similarly, what if I run a simulation with 1 millidarcy? Well, here's what it looks like, and here's the plot of dPdG. Again, it's pretty much just continuously going down the whole time. And so if we have rapid closure, that rapid closure will happen so fast that it basically just looks like the PDG is going down the whole time, because basically pressure is falling off so fast that we're getting deviation from Carter leakoff very rapidly. We'll also see things like, we never really have a flat period, so derivative can't increase because of closure is happening kind of immediately. That doesn't necessarily mean that we're going to see radial flow at late time, because like in this case here, we have leak off into these linear features. We might still see linear flow at late time. So that's a challenge. And I think probably the most concerning problem is going back to this problem of near wellbore tortuosity. So remember that near wellbore tortuosity can cause this elevated pressure. So in this case, it's okay because near wellbore tortuosity ended and then later the fracture closed. But what if this fracture had been closing much faster because the permeability was higher? What if the fracture was closing here at the same time that near wellbore tortuosity was still taking an effect? In that scenario, you don't have a good way of estimating stress. You cannot estimate stress because near wellbore tortuosity is still happening when the fracture closes, and it covers up the real reservoir response. So that is unfortunately an uninterpretable well test. And so how do you know whether or not you have near wellbore tortuosity? Well, the conservative and rather dissatisfying answer is that if you're in a horizontal well, you probably have near wellbore tortuosity. So if you're in a horizontal well and you see this monotonic signal, it's ambiguous. You don't really know when the fracture closed and how that's related to the near wellbore tortuosity. It's definitely a frustrating and unsatisfying answer. And then also another potentially, so that's pretty much my answer, is you may not be able to estimate. Now, if you have a vertical well, especially if it's open hole, you should feel very comfortable in an open hole vertical well that you're not going to have near wellbore tortuosity unless it's a reverse faulting regime, which is not common. And in that case, you can make this estimate. So that's just an unfortunate reality of it, and there may be ways to get around this problem, but I don't have a perfect solution for it. So in the roughly 1/4 to maybe 1/3 of DFITs where I see a response like this, I usually say I cannot interpret stress, which is unsatisfying, but that's just the answer. I think that's the reality. We shouldn't claim to estimate stress if it's not possible to estimate stress. Now, I also noticed this happened a lot in the Bakken in particular, and I think it's probably because the Bakken has a higher permeability than most other shale plays. And so it's more likely that the fracture will close simultaneously with near wellbore tortuosity. One other point I want to point out here, what if you pump a large volume and then a small volume? Here's a published example. So the first test, we see a very strong compliance method closure response. The second test, we don't. So what happened here? When you inject the second time, do I have a movie of that? No movie. You're reopening this larger feature, and it never fully opens. And then when you shut in, if you injected a smaller amount than the first injection, the fluid just rapidly spreads out into the rest of the pre-existing hydraulic fracture. That's an instant closure response. So this is very predictable, and I've seen many examples of this. I would even hazard a guess to say that this will nearly always happen if you inject a large volume and then a small volume. The second injection, the lower volume, is injecting into a bigger system. It has instant closure, and you'll get these monotonic DPDG responses, even if you have a very clear response the first time. So that's an important thing to keep in mind. And generally speaking, if you inject a large volume and then a small volume, you cannot interpret the second injection's results. At least you can't interpret them for stress. If you do, it should be instant closure, and then you have to ask, what do I know about near wellbore tortuosity? If there's any risk of near wellbore tortuosity, it could be happening simultaneously with closure and cover up your ability to estimate stress. Okay, so important point here, if you are estimating permeability from a DFIT, you are estimating the permeability to the mobile reservoir fluid. So it's not the absolute perm. If you think that the oil rel perm is 0.2, then you're estimating absolute perm times 0.2. Very important to keep that in mind. Okay, so how about post-closure transients? We've talked a lot about interpreting closure and pre-closure. What do we do at late time? We like to do 1 week shut-ins, right? That's about 10 to the 4 minutes. What do we do at late time? So I recommend using log-log plots. And the log-log plot, the key curve here is this red line. It's the derivative of pressure with respect to the logarithm of shut-in time. I want to make an important point. Sometimes we see people take those lines, we take the derivative with respect to something called superposition time or Horner time. That is a method that was developed for conventional well testing that makes assumptions and is based on mathematical properties that are not applicable to a DFIT. So I explicitly do not recommend that you take the derivative with respect to superposition time, Horner time. I recommend you take it simply with respect to time and interpret the test in that way. If you take the derivative with respect to superposition time, it introduces kind of an extra weird bend in the curve that doesn't mean anything. It's a mathematical artifact. It just confuses people. So I don't recommend that. When you hear people use the term Bourdais plot, also confusing because sometimes they mean Bourdais plot just means a log-log plot like shown here. Or other times people will insist that a Bourdais plot actually suggests that you're taking the derivative with respect to superposition time. So you just have to be really careful and be aware that when you look at these log-log plots, terminology is confusing. Often people don't clearly label it. They may or may not be taking derivative with respect to superposition time. If they do take derivative with respect to superposition time, what it does is it kinks up all the slopes by 1. So this -1 slope would be flat, a -1/2 slope would be a 1/2 slope, etc. So you got to be really careful about that. And I have a paper called the spurious deflection on superposition log-log derivative plots, in which I talk through why this is a theoretical issue and why you shouldn't do the test. So anyway, I just want to make that caution. Okay, the beauty of taking derivative with respect to actual shut-in time is that there's a very clean physical meaning, mathematical meaning. If there's a -1 slope, that means that this pressure change is scaling with time to the -1. If it has a -1/2 slope, it means that the pressure change is scaling like time to the -1/2. And generally speaking, a -1 slope is conventionally interpreted as representing radial flow, and a -1/2 slope is conventionally interpreted as representing linear flow. Very important finding from our DFIT study is something called false radial flow. What we found is specifically when you have a viscosity contrast between the injection fluid and the reservoir fluid, and that would occur typically in a gas shale where the gas is much less viscous than the water that leaks off. That viscosity contrast combined with the effective closure and the onset of impulse flow results in something that looks like radial flow. That's a -1 slope in a gas shale DFIT. That is not actually radial flow. And if you use that to estimate permeability, it results in about a 100x overestimate. And that can lead to really suboptimal designs. So that's an important finding that we got from the study. Okay, lastly is pore pressure, and this is not a very, nothing here I'm going to say is a new idea at all. This is actually a good analogy to classical well testing. So in classical well testing, if you injected and then shut in, here's the equation for impulse linear, here's the equation for impulse radial. Here we see that 1/√1/time signal. So again, be very cautious about these impulse radial. I think in a DFIT, it's quite uncommon to see a genuine radial signature. And if you do, it should be a very low volume of injection, like maybe 10 barrels, and the permeability might need to be, 500,000 nanodarcies. So if we took, for example, a test that had a impulse linear signature shown as a -1/2 slope on the log-log plot, we could make a plot of pressure versus 1/√of time. So here's an example. This is just a simulation. Here we have a very clear and strong -1/2 slope on this log-log plot that indicates linear flow. And by the way, that may not look like a -1/2 slope, but you just have to kind of look at the axes. So here we can see the separation of one log cycle on the y-axis is greater than the separation of one log cycle on the x-axis. So even though visually that doesn't look like a -1/2 slope, if you look at the scale, you can see that it really is. All right, so here we've identified a linear flow period. Then we can make a plot of pressure versus 1/√of time. And what we do is we just extrapolate that line out to 0. That represents infinity time, and that's the pore pressure estimate. This is a simulation. We know that the simulation pore pressure was 7,000 psi, and sure enough, the technique gives exactly back the correct pore pressure estimate. So that is classical method. Everybody does that with DFITs, and we do that as well. So no changes to conventional technique here. Another thing, this is a minor topic, I recommend smaller volume DFITs. And there's two reasons. First of all, you really would like to get a good pore pressure estimate, right? And the more fluid you inject, the longer it takes for you to get out to this impulse transient. A lot of times I get DFITs and they shut in for a week and they've only gotten up here and it hasn't started to come back down yet. And the reason for that is because if you inject 50, 60 barrels or more, it just takes longer for everything to happen. And so if you keep the volume small, like 15 or lower, you're more likely to get out to impulse transients. A second reason is that there's less uncertainty about fracture geometry. So when we do the permeability estimate, we have to assume something about fracture geometry. And if you only inject like 10, 15 barrels, you can probably assume it's a pretty radial fracture. Versus if you injected 100 barrels, it's more likely that the crack has hit stress barriers and we don't really know where they are. And so the bigger the crack gets, the larger volume of rock it's sampling and the more complicated everything gets. And so if you keep the crack relatively small, it's probably radial, it's probably not crossing a whole bunch of different zones, and you're going to get a more kind of concrete estimate. I've seen, conversely, some people advocating the opposite. So I've seen very large volume DFITs advocated, like 300 barrels. The philosophy behind that design is they want to create a really big fracture to sample a whole bunch of rock to get a really robust estimate. I don't really ascribe to that. I don't think that if you sample a huge volume of rock, you might in fact just cross a whole bunch of different layers, and Earth is heterogeneous, and so that's not really helping you. You don't really know what the fracture geometry is anymore, and you're trying to get one single point measurement. It's not really helping you to try to sample a whole bunch of different layers and somehow average that into one number. So I don't recommend that. One other point I'll make here, sometimes you're in an under pressured formation. What that means is that at some point the wellhead pressure gets to zero or to atmospheric pressure. And at that point, and that'll happen because the pore pressure of the formation is below hydrostatic. If that happens, the storage coefficient of the system changes because now what happens is the level of water will start to fall. So like water will not reach the top of the well anymore. That completely changes the storage coefficient and will make it impossible to estimate pore pressure. So that's a very annoying problem. It doesn't matter how much you inject. If you hit hydrostatic, that's still gonna kill you. And I've seen field tests where they don't get out to impulse in time and they hit that what you might call vacuum at the wellhead. That's a frustrating problem. The only ironclad solution to that is to use a downhole shut-in tool. Of course, that itself is expensive and is not that common, but it's possible to avoid it, but that's the solution. Okay, so to summarize this, I just went through the step-by-step DFIT interpretation procedure. Even though this is about a 2-hour talk, still, I didn't cover everything in total detail. Feel free to refer to the paper with more detail. The paper also has mathematical derivations and explains the references and how everything is done. The goal here is we believe we've identified improvements to accuracy and estimation for stress and permeability. We're accounting for things like near wellbore pressure drop, the effective imperfect mating, extended and combined methods from Valko and Economides, Mayerhofer, added in our own twist to include things like wellbore storage to get better permeability estimates. Important finding is that in gas shale, specifically gas being the key word there, false radial and the DFITs can cause a large overestimation of permeability. That has a big impact on economics. You can incorrectly space your wells and incorrectly space your clusters. And actually, there's quite a few additional details in the paper I didn't cover there in the paper that I encourage you to check out. All right, one last step or one last little section of this talk. I'm going to talk about some of the curveballs that I see in real data. So within our company, we do a decent amount of DFIT interpretation for clients and see all sorts of problems and things that trick us or trick the client or trick somebody. And we have to constantly be vigilant to make sure that we are on top of this stuff. So here's a few of them. First of all, when you actually get field data, it's usually pressure every 1 second, and it's usually not synced up with rate data. So you'll get, you might get an Excel spreadsheet that has a lot of rows in it, hundreds of thousands of rows, and it has just columns for pressure. And so when you start doing an interpretation, you have to identify shut-in, right? That's a pretty fundamental thing to start doing things like calculating the G-function plot, making plots. You have to find the point of shut-in. It's harder than it sounds. When you have 100,000 rows, just scrolling through the rows, it's going to be a little hard. And you also might sometimes see things like if they did a step down test. So you might see one row and then suddenly the next row has a lot lower pressure, and you might say, oh, okay, well, that must have been shut in. But actually, it's just a step down. So what I always recommend doing, first thing you should do is just make a plot, just in Excel, pressure versus time, and just visually observe what that curve looks like. So you can just see at high level, what are you working with here? And then I recommend identifying the shut-in time by just visually looking at this plot, and then you go down to the actual table and you can identify it. So like right here, just to have an example, we would see from 19 to 20, there's a big drop in pressure, and so we could say, okay, this must have been the last point of injection. In this case, it's really simple, but it's not always so simple. It's really important to kind of cross-check the visual plot with the data here. Another thing to keep in mind is a lot of time when you shut in, you see pressure oscillations called a water hammer. And so that can also make it confusing. If you're only looking at the table, pressure might look weird in the 1 second data. You really need to look at the plot to see the overall trend of the data and just manually identify when shut-in occurred. It'd be great if they would just tell you rate versus time and you could just find the place where rate went to 0, but they usually don't. Or, this is very important to keep in mind, very often, if you do get rate data, it may not be exactly temporally synced up. So somehow, I don't know how, but a lot of clocks get really out of sync out there in the field. And so if you get data from different sources, different gauges, you have to be very vigilant and concerned that the times may not be exactly synced up. All right, secondly, you might have missing data. We've gotten data like this where they had 1 second data or 1 minute data, either way, usually 1 second data. And so I might say, oh, cool, I'm just gonna, to make it easy to make a plot in Excel, I'm just gonna, make a column where I have, every row representing a 1 second increment. But then out of the blue, they just skip, 5 minutes. It'll be adjacent rows, no gap, no indication. And so if you don't account for that, you could get something crazy like I see here. So here what happened is I took this data, I assumed that every row was 1 minute, made a plot, and we saw an abrupt drop in pressure. The problem is that turns out there was just one particular pair of rows where they weren't separated by 1 minute. So actually, this is what the data should have looked like. This is the kind of thing that you'll just see all the time. You just got to be careful about it. You also can see stuff like this. You can see just at some point in time there isn't anything reported, or it might have text like no data, or you might just have a gap. And all of this is a mess because if, like for example, I often use Python to import this data, and Python will get really confused trying to import data like this. Python also tries to infer what type it is. So it might say, oh, okay, well, this is a number, this is a number. And then it sees that and it says, oh, this is not a number anymore. And it treats it all like strings, and then it causes the script to crash. So it's going to be really paranoid about this kind of thing too, that it's very often just a little bit inconveniently provided by the service company. Missing rows, text randomly stuck into things where there were numbers, etc. Another thing is you should just be really careful about units. It's very common for people to not label units. And of course, time could be seconds or minutes. So you just have to be really careful about that. And if there's ever any ambiguity, don't hesitate to ask. Another example here is I've got pressure. Is that wellhead pressure or bottom hole pressure? And not just bottom hole pressure, but if they give you bottom hole pressure, where was the pressure gauge actually set? Because bottom hole pressure doesn't always literally mean bottom hole pressure. It means bottom hole pressure means pressure at the location of the bottom hole pressure gauge, which might have been 300 feet above the actual TVD. So you've always got to ask if you get bottom hole pressure, hey, is this the bottom hole pressure I should use that represents the pressure at the toe or at the injection point or not? And of course, you need to do a hydrostatic head adjustment if not. You should also, if you get wellhead pressure especially, you should ask for specific gravity. Ideally, they would use fresh water, but if they have a highly saline fluid, that could cause problems. Or you could have a specific gravity of 1.05, and that can have a non-negligible impact on the bottom hole pressure calculation. So got to be really paranoid about that as well. Another thing is TVD or MD, just basic stuff here. But we've got if you have a horizontal well where they drill down 10,000 feet and then they drill 10,000 feet over, then you know that TVD and MD are really different, right? MD is probably 20,000, TVD might be 10,000. But if you have a mildly inclined well, or you've got a test from kind of the part where they built the angle, TVD and MD may not be that different, and it may actually be ambiguous which one they're referring to. So nevertheless, you'll get a depth that doesn't say which, and you got to be super careful, especially because you often will want to be reporting your data in terms of like PSI per foot, either the frac gradient or the pore pressure, and so you don't want to use MD when it's TVD or vice versa. So sometimes not given clearly, just never hesitate to ask for clarification and make sure. Never make assumptions in this stuff because it's really easy for stuff to happen. That mixes you up. Sometimes you see abrupt changes, like right here. We shut in and then, why did pressure go back up? Well, let's just not forget that a lot of things that happen aren't really pressure transients from the reservoir. So one thing that can happen is maybe they switched from one pressure gauge to another, and those pressure gauges are slightly calibrated differently, or maybe once, etc. And so maybe what happened here is that they're actually amalgamating two different series of data, and there's a slight inconsistency there. Or who knows, really? I mean, ask them operationally, what do you think could have happened? But don't go crazy trying to interpret something like this. That's not a real DFIT pressure transient. That's related to some kind of operational something, and you either have to just ignore it, or if you see really severe abrupt changes, it could be an impact from an offset well. Like what if you're doing a 1 week shut-in and an offset well is hydraulically fractured? There could be poor elastic response that you see, right? So if you see weird, sharp changes and you can't explain them, then you should not interpret them. Don't try to interpret things that you don't understand that have probably happened because of operational things that are out of your hands and you don't have information about. Another one is defining the injection volume. So you got to be careful here. First, often they'll do some like pressure testing prior to the DFIT. So here they may have like a toe valve. They're going to pressure up a little bit, just make sure pressure holds, and then they release that pressure. This is injection, but don't include that in the injection volume of the DFIT, obviously. Now, another thing is sometimes they might report injected volume as here, like here's where the valve opens, so they're going to count only the injection here. They're not going to count the injection prior to the opening of the valve. So you just got to be careful and make sure you ask, because when, like in our DFIT interpretation procedure, we're accounting for wellbore storage, and frankly, you could start the interpretation from here or here, but you need to know which it is because you need to account for the wellbore storage. So if you count this injection as total injection volume, then in our interpretation procedure, we ask for a wellbore storage coefficient. We ask for the initial pressure at the beginning of injection, and it would account for that wellbore storage. So you just need to make sure that you know when you're talking about injected volume, was it from the actual start of injection or was it from the breakdown? Very important. Another one is pumping down the perf guns. So remember I talked about here, if you inject a large volume and then a small volume, when you inject the small volume after the big volume, you get an instant closure response because you never really fully reopened the crack to begin with. Well, I've seen DFITs like this where they pump down the perf gun, and the act of pumping down the perf gun is creating a giant hydraulic fracture because they have a wet shoe, and then they fracture, and then they pump a little more, and you get a test that looks like this. In that case, pumping down the perf gun, that's the DFIT. Even if there's a 1 hour gap between pumping down the perf gun and doing the perfs, you should use that as the DFIT. You'll probably see a response like this rather than like that. So you got to be really careful about that. It's obviously not recommended. Basically, if you're going to do a DFIT, make sure that you haven't already injected into that block of rock. You're not just re-injecting into a fracture that already exists. If you do, it might be okay if you inject it a little bit and then you come back later and inject a lot. But anytime you inject a lot and then come back later and inject a similar amount or less, that's going to profoundly impact the DFIT. All right, another thing to keep in mind here is formation dip. So what if you have multiple DFITs in different wells and you want to compare them? So first off, this is why you should always calculate gradients. You should always divide by depth, TVD, in order to get an apples to apples comparison. But the second thing is that you can't just plot, stress gradient versus depth in 4 wells, because shales are not typically too structurally complex for the most part, but they do have dip, and so you might have one well that's at 9,900 and the others at 10,000, those are actually smacking the same with formation. So what you really want to do is you don't just plot stress, frac gradient or pore pressure versus depth. What you want to do is you want to figure out what formation each of these DFITs was performed in. And then what you might do, like what we've done here in this plot, we've created a reference depth, not literal depth. So what that means is we've said at a particular location, this is in fact the location of the formations versus depth, right? And then we know we have 4 dots here representing 4 DFITs. They were performed at these locations in those 4 formations. So we're saying if they had all been performed at the same location, this is the depth that those DFITs would have been performed at. And so here we've made kind of an effective plot showing this trend of stress versus depth. But if you just plotted frac gradient versus literal depth, you could end up with some really misleading results. Like maybe these dots all end up at the same place, and then you're really confused. So got to be really careful about that. Another example, I referred to this earlier, but even if a fracture doesn't form, G times dP to G has to go up, and then it has to go back down. Because when G is equal to 0, this is equal to 0, and at late time, the derivative goes to 0. So here's a nice example from some tests performed at the recent Forge project. At the very beginning of their sequence of injections, they never reached the breakdown pressure, and we can see that here in the injection data. Pressure never flattened out, but they are actually demonstrating pretty nicely that you can still make a G times dP/dG plot, and there's still a theoretical, you could make a closure pick even though there's no fracture. So just be aware that make sure you actually made a fracture before you estimate stress. Otherwise, like in this case, you would arrive at an extraordinarily low stress estimate. All right. So thank you for making it through this very lengthy talk. I hope you found it really useful. I'm always happy to answer questions and discuss. Really appreciate that. So feel free to reach out to me, mark@resfrac.com. And also, we'll know we reproduced a lot of figures from SPE papers. We, in fact, did request permission from the SPE and, in fact, paid to have the right to represent these papers, those figures in this presentation. So those are reproduced with permission. And also, here is a list of some of the papers referred to in this talk. Some really outstanding work by some brilliant engineers, of course, have influenced a lot of the stuff that we're showing today. So thank you again. Really appreciate it. And again, always happy to discuss. Feel free to reach out. Thanks so much.